This is Unit 7, Video 1. In this unit, we will be focusing on liquids and solids and the energy changes associated in going from a liquid to a solid and a gas as well. So, let's begin. Now, the previous chapter was over gases, and recall that we said gases, what distinguished gases from liquids and solids, is that gases did not have any attractions for each other. The particles had no attractive or repulsive forces. And this was the third point, one of the assumptions of the kinetic molecular theory of gases, what made gases into gases. And then this is what distinguishes gases from liquids and solids. Solids and liquids have these intermolecular forces. And remember, we said that the way you can make a gas into a liquid is by either cooling it or compressing it. And by cooling it, these intermolecular forces come into play. Or if you compress it, the molecules get close enough to where they begin attracting each other, and then it no longer behaves as a gas. So intermolecular forces will be the discussion for this chapter. We'll be pointing out intermolecular forces quite a bit. And let's kind of review them. We've looked at them a few times already. So intermolecular forces, remember, are the bonding forces between molecules. You could think of these as physical bonds. They influence the physical bonds of substances. Now, there is something called an intramolecular force. That was the force inside of a molecule. These are the bonding forces between atoms. So this here, it would be a chemical bond that holds hydrogen and chlorine together. And then this here would be a physical bond that holds the two molecules together. And so if you want to ask whether this is a substance is a liquid or a solid or a gas, you have to ask how strong are these forces that keep the molecules together. And that's what we'll be focusing on. They are the intermolecular forces. And as a review or a restatement of the same thing, in a chemical change, the intramolecular forces are broken. The inside forces inside of a molecule. So for example, if you want to split water, here we have a little experiment which would hopefully you've seen. If you want to split water into oxygen and hydrogen, you would have to undergo a chemical change. And there you would be breaking intramolecular forces. But if you want to simply boil water, so here we have just water becoming a gas, going from a liquid to a gas, this technically is a physical change. And here you're breaking intermolecular forces. So the difference between a chemical and a physical change oftentimes can be seen in these two types of forces. So we've studied these in previous chapters, so we'll come back to them as well. But here we're going to focus much more on intermolecular forces. And here are the three intermolecular forces again. They are also known as van der Waals forces. And the neat thing is that van der Waal came up with the non-ideal gas law equation that makes gases behave less like gases and more like liquids, essentially. And he came up the first to kind of identify these three different forces, categorize them. And the first, remember, is the dispersion force. And this is operating in nonpolar molecules. And it depends on the size of the molecule. The bigger the molecule, the stronger this force, because you have a bigger electron cloud and the electrons can be dispersed more to one side, creating more of a negative side and on a positive side. Dipole-dipole forces are permanent forces essentially on the molecule, and that comes from the polarity of the molecule. If the molecule is polar, you'll have these dipole-dipole forces. And then the strongest of all, if you recall, were the hydrogen bonding, which is present in three cases. You have fluorine, oxygen, or nitrogen connected directly to a hydrogen. And recall that this force is the force that results when a neighboring molecule essentially attracts through the hydrogen to the electronegative element. It's this force here that is called the hydrogen bond. Not this. This is not the hydrogen bond. And here we have a picture of what we mean by forces. So you have two molecules here, and these forces create a partial negative charge, a partial positive charge, and then that's why the molecules attract each other. So these partial negative charges, partial positive charges, in dispersion forces, then these would be temporary negative and positive. They're just set up temporarily. In a dipole-dipole force, they would be permanent, this negative and positive, and in the hydrogen bonding, they'll be extreme. And we said that hydrogen bonding is like an extreme version of the dipole-dipole force. Okay, a quick review. I've got a few more notes about this, and especially with hydrogen bonding, because hydrogen bonding is a very strong intermolecular force. Compared to the other two forces, hydrogen bonding is very strong, and it's able to do some interesting things in chemistry and then in biology, actually. So you get HF, HO, and HN, and it turns out in biomolecules you see a lot of these bonds. You see a lot of HO bonds, you see a lot of HN bonds, particularly in amino acids, proteins, DNA. Those are what are called macromolecules. And these contribute significantly to the folding in these big biomolecules. Very famously in DNA, you hopefully have seen DNA or studied it already to some extent. You have the two strands of the DNA double helix, and they're connected through these bases. And you know that a G connects to C and so forth, but the connecting of the two strands, two rungs of the ladder, as they call them, is done through hydrogen bonding. Hydrogen bonding is actually key in order to keep the double helix together. So what keeps the double helix of the DNA molecule together are hydrogen bonding. Proteins also are made of, they have helices. It's called an alpha helix, very similar idea. And beta sheets, you may have studied proteins in more detail. And these structures, the helix in proteins, the sheets in proteins, are also held together by hydrogen bonding. So H bonding is extremely important. And if you study these bases on the nucleotides of DNA, what you'll see is nitrogens and hydrogens and oxygens and hydrogens on it. So that's a little connection to good old biology. London dispersion forces, here is a tip about them. They are present, remember we said, in all molecules, because as long as you have electron clouds, you have dispersion forces. And even though they're the weakest of all, they could get quite strong if the molecule gets quite big. So here it says they contribute significantly to the phases of big molecules, so large molecules, big meaning big electron clouds, which means high molar mass. And this is especially true of oils. So an oil molecule is actually a pretty big molecule, and oils are nonpolar, that's why they don't mix with water. But if you have ever tried to boil an oil, it is pretty difficult. They have very high boiling points. Oils usually don't boil so easily. You can easily boil many other lighter substances, lighter molecular mass substances, before oil boils away. All right, so these are a little more in-depth study of the two forces. So, as a quick example, tell which intermolecular forces are present between these molecules. Now, I've drawn them out, and remember, we have drawn the Lewis structures of these, so be prepared to possibly draw some Lewis structures throughout the chapter. But the Lewis structures drawn out allow you to see if the molecule is polar or nonpolar. And polar or nonpolar, remember, relates to if it's symmetrical or not symmetrical, for the most part. So because this is symmetrical, CF4 is symmetrical, it should be nonpolar. And if it's nonpolar, all it has are London dispersion forces. Good. Because this one is polar, you have the hydrogens asymmetrically arranged around, because there's no hydrogen up here, because that's empty. What you have is you have an overall pull of phosphorus toward itself. You actually have what's called a dipole, and the dipole has the negative side toward the phosphorus, the positive side on the hydrogen, and you get yourself a polar molecule. So this guy is polar, slightly so, but it is polar. And so if it is polar, then you've got yourself dipole-dipole forces. Now remember, everything has London dispersion, so then these also have London dispersion. And then finally, famously, a very similar arrangement, but if you put nitrogen into the mixture, you get yourself hydrogen bonding. Because nitrogen is extremely electronegative, it's able to pull the electrons so far off the hydrogen that hydrogen essentially gets exposed, because it only has one electron, and that electron gets pulled off, creating a very positive side to that molecule, and you have H bonding here. And so it is polar. We can also say it is polar, so it will have dipole-dipole forces. So it must have London dispersion because it's a molecule, and then famously it'll have hydrogen bonding. This is good old ammonia. Ammonia is a good molecule to know the structure of, in case you get asked on the street or at a party. You can refer to the hydrogen bonding nature of ammonia and similar molecules. Okay, here's a quick little practice. Go ahead and pause the video, try it, and then we'll wrap up this video talking about some physical properties that are a result of these intermolecular forces. So here it says the strength of the attractions between particles can greatly affect the properties of these substances. So we'll talk about especially liquids. We're going to focus on liquids here. So we'll talk about boiling point in this video, and in the next video we'll talk about things like viscosity, surface tension, latent heat, specific heat, and so forth. So these are physical properties, and they come from the intermolecular attractions, the attractions between the molecules. So if these are molecules, then it's this attraction that we're talking about here. Okay, let's take a look at boiling point. A boiling point is a good measure of the strength of the forces between molecules. So here we have 3 examples, and the 3 examples are fluorine, diatomic fluorine, F2, bromine and fluorine bonded together, so you can say bromine monofluoride, and then we have hydrogen fluoride. Now, what you'll see is that fluorine, diatomic fluorine, has a really low boiling point, quite a bit below room temperature. Bromine and fluorine have negative 20 for the boiling point, so it's still a gas, but not as bad. So, but however, HF is actually almost a liquid, so its boiling point is 19.5. So you can actually get this to be a liquid pretty easily. Just create some, lukewarm water, or not lukewarm, cool water. Lukewarm would be more like 30, 40. Some cool water, and it'll liquefy. So you could see this has hydrogen bonding. This is polar, and this is nonpolar. So you can see that progression from London dispersion forces to dipole-dipole to hydrogen bonding forces. And water famously has an unusually high boiling point, and we'll see this in a graph here in a minute. And that's because it has hydrogen bonding, and that's a good thing. We don't want water to boil at a low temperature because water is so important to life and to the processes on the Earth. We don't want it to boil away before that. So size of molecules also have a big effect on the strength of these forces, and so the boiling points. So the bigger molecules and also the longer molecules, if you have a longer molecule, they'll have stronger forces than smaller spherical molecules. And the longer and the bigger the molecule, the dispersion forces increase, since you have a bigger electron cloud. So if you just take a look at dispersion forces, and these are the halogens, this is the series of halogens, from fluorine to chlorine to bromine to iodine, the electron cloud increases in size, so the strength of the forces increases, and lo and behold, the boiling points also increase. These boiling points are given in Kelvin, but again, we've seen fluorine, very, very low boiling point. Chlorine is actually not too bad, even though it's quite a bit below freezing, but you can actually liquefy chlorine quite easily by decreasing the temperature. And then bromine is finally above freezing, above room temperature. So, and then iodine is a solid, very, very high boiling point. And so you can see this progression. And also if you have a long molecule, so if you have a spherical molecule like so, and then you have a long molecule like so, the long molecule, if it has a similar molar mass, will actually have a higher boiling point. And that's the other issue here. Polarity can also be looked at, and you can take a look at the boiling points of polar molecules. So here we have a bunch of molecules. Now the polarity is actually given by something called dipole moment, this little Greek symbol mu. And don't worry too much about it, we're not going to do too much with this number, but what you see is that we've picked a bunch of molecules where progressively they get more and more polar, but their molar masses, molar weights are about similar. So molar weights are looked at when you want to take a look at London dispersion forces. So we'll say roughly the London dispersion forces are comparable, but because they get more and more polar, you see that boiling points increases. And again, this guy here, acetaldehyde, this guy here is close to room temperature for being a liquid, and this guy is definitely a liquid already. And that's the idea. And because if you're polar, then you have these attractions, you have these permanent dipoles that set up permanent negative, permanent positive side, and then you get attractive forces between the molecules, both vertically and horizontally, as you see here in the 2 diagrams. Now, and then let's take a look at hydrogen bonding in a little more detail and how that affects boiling points. What we see here is we have water that is graphed against similar molecules. So if you take, from the periodic table, if you take oxygen's group, group 16A, and here's oxygen, and then if you take a look at sulfur right below it, selenium right below it, and then tellurium right below it, if you make analogous molecules between, dihydrogen telluride and dihydrogen selenide and dihydrogen sulfide and dihydrogen oxide, water, if you compare them, water is completely off the chart in terms of its boiling point. And this is very interesting because water should essentially, be maybe somewhere here, or if you follow the trend, water's boiling point should be around negative 100, but it's actually 200 degrees higher, about 100 degrees Celsius. And especially if you take a look at a similar nonpolar series, they follow the expected trend. There's kind of an expected trend a little bit. CH4 is all the way down here. Turns out CH4's reduction in just molecular size causes this big decrease because it's really carbon's just has a few electrons in it, so it really decreases in strength. But water, we should see a similar effect with water, but it goes the opposite way. Whereas CH4 goes down from the trend, water goes up from the trend. So water has hydrogen bonding, and that's how significant hydrogen bonding is. Quite an anomaly, and thankfully so, because water can be used as a substance to build life and ecosystems on and so forth. So this is a famous graph that's shown to really point out hydrogen bonding. All right, we'll finish up with this example. And here it says, predict which would have the higher boiling point and give the reason for it. So here we have CH4 versus CH3OH. So hopefully, just the way this molecule is written, you can see that we have hydrogen bonding here. So if you have H bonding, then this one will definitely have the higher boiling point. In fact, this is called methanol. Methanol is a liquid at room temperature. And this is methane. Methane is the gas that comes out of our gas jets in the chemistry laboratory. And this is definitely a gas. So methanol has a higher boiling point. All right, if you take a look at two molecules that it looks like they don't have any polarity to them or any hydrogen bonding, then you would pick the one with the bigger formula, because then you have a higher molar mass, so you have a bigger electron cloud. So definitely this one, and you can say bigger molecule. Bigger molecule. Molecule. And so stronger London dispersion forces. Because remember, London dispersion forces depend on the size of the molecule. Okay, this wraps up video 1. We'll take a look at some other properties in video 2.